Have you ever wondered how you can have like a dozen tabs open, music playing, and a game running all at the same time without your computer just completely giving up? Well, in this explainer, we're going to dive into the secret behind that magic, something called memory management.
It's a great question, and it really gets to the heart of how modern computers work. The secret isn't just about having raw power, it's about an incredibly smart strategy for managing the computer's most critical resource, its memory. So let's pull back the curtain.
But, before we get to the solution, we've got to understand the problem it's solving. And that problem starts with the brain of the whole operation, the central processing unit, or the CPU.
A CPU has one single, relentless job: to execute instructions. It is a processing powerhouse, and it's designed to be busy all the time, just chewing through the code of your programs at incredible speeds. Its ideal state? 100% busy 100% of the time.
Okay, but here's where the problem kicks in. What happens when a program needs to do something that, in the computer world, is agonizingly slow? We're talking about things like input/output operations, or I/O for short, like reading a file from a storage drive. So, for a lightning-fast CPU, waiting for the hard disk is kind of like a Formula One driver being forced to stop mid-race to wait for a bicycle career. The CPU literally has to slam on the brakes and just wait. It becomes idle. And an idle CPU is a completely wasted resource. It's the ultimate inefficiency. So, how does the operating system, the OS, get around this massive inefficiency problem? Well, it uses this really clever strategy called multiprogramming. The main idea here is to increase something called the degree of multiprogramming. In simple terms, that just means the operating system loads as many different programs or processes as it can possibly fit into the computer's high-speed workspace, which is the RAM. And this is where the magic really happens. Now, when process A has to pause for that slow file, the OS doesn't just let the CPU sit there twiddling its thumbs. Nope. It instantly switches the CPU's attention over to process B, which is ready and waiting in RAM. Then, if B needs to wait, it might switch to C, then to D, and then eventually circle back to A once its file is ready. The point is, the CPU is never left idle. It's constantly being fed new work, pushing it toward that 100% utilization goal.
But to make this whole juggling act possible, the OS needs a really smart way to organize everything in RAM. And this leads to a fundamental choice between two competing strategies, two different philosophies for how to arrange all these processes in memory.
So, on one side, we have the keep it all together approach, which is known as contiguous allocation, and on the other, we've got the split it up and scatter it method, called non-contiguous allocation. Let's take a look at each one.
All right, first up is contiguous allocation. And just like the name says, it means continuous. The entire process gets stored in one single unbroken chunk of memory.
So just imagine a program is made up of several internal parts or blocks. Well, this method says that all of those parts have to be stored together in RAM as one solid block, taking up one continuous space.
Now, this whole idea has evolved over time. Early on, you had something called fixed partitioning, where RAM was just divided into these static, pre-sized boxes, and a program had to fit into one of them, period. A more modern take is variable partitioning, where the OS carves out a perfectly sized block for each program exactly when it's needed, much more flexible.
Okay, so the other path is non-contiguous allocation. This is a far more flexible strategy, and it's really at the heart of how modern systems manage memory.
With this approach, instead of treating the program as one giant indivisible block, the OS first breaks it down into a bunch of smaller, more manageable pieces. So, let's say we have our program, process P. It might get split into 4 different pieces, P1, P2, P3, and P4. So now the OS has 4 little chunks to work with instead of one big one.
And here's the really cool part. The OS can now place these individual chunks wherever it finds a free spot in RAM. A piece of your browser could be at the very beginning of memory, while another part is way off in the middle somewhere. The same program is physically scattered all over the place. So there we have it, 2 very different strategies. Keep it all together or split it all apart. And this brings us to the crucial trade-off, and why this choice directly affects how fast and responsive your computer feels every day.
This really lays out the central conflict perfectly. Contiguous allocation? It's simple. It's fast for the CPU to find everything, but wow, is it wasteful.
I mean, think about it. If a program needs a 10 megabyte block of memory, but all you have are two separate 5 megabyte gaps, you're out of luck. Non-contiguous allocation solves that by using up all those little leftover gaps, super efficient. The downside? It's way more complex for the OS, which now has to basically act like an air traffic controller, keeping track of where every single piece of every program is.
This decision, this choice, which is happening millions of times a second inside your device, directly impacts its performance. It determines how many apps you can run at once and how responsive and fast the entire system feels. It's really the silent engine of multitasking.
So, which strategy is running the show on the device you're watching this on right now? Well, the truth is, modern operating systems use incredibly sophisticated versions of that non-contiguous split and scatter method. They've decided the extra complexity is absolutely worth it for the massive gain in efficiency. And understanding this core trade-off between keeping things simple versus being incredibly efficient is really the key to appreciating the invisible, complex dance that allows your computer to do so much